morning. My name is Adrien BARBOT. I'm from KRONO-SAFE, a small company near Paris. What I want to stress out from the beginning is that we provide a real-time kernel, but that's not important. It's a small part. What we provide is a tool chain for designing new applications, and that's what I will talk about and the qualification that goes with it. The previous presentation showed us that you already know how to express your functional requirements and how to qualify your code with that. So there are many solutions on the market. There are new solutions on the market. So you know how to do that, and we won't help you doing that. That's your problem. But for other aspects, like temporal aspects, for special segregations, for your error management, usually you don't have a unified model to express that and generate automatically what you want on your operating system level. So in this schematic, I've shown that from your system specification, you derive a platform specification that goes into a hardware and operating system development on one side. And on the other side, you have your application with your functional aspects. And these functional aspects usually goes into three categories. The first one is how you will be able to configure your operating system to match your requirements. So let's say, for example, that you want your function to output something every 10 milliseconds or every 2 milliseconds. You will have to design some tasks in your system, put some priorities on them, and make the demonstration that you will output your data every 2 milliseconds or every 10 milliseconds. On the market today, you don't have a unified language to express that. That means that you will have to put that into words in English, and somebody will have to take into account the operating system you're using and configure it accordingly. So meaning create the right task or create the right A653 configuration items to match your requirements. And then you will have to demonstrate the compliance. On the other side, you will have your functional aspects, for example, with model-based design, like it was presented a moment ago, or manual code, because we all know that we can't put everything into models, so there is always some part that remain on the side. The main issue with that is that when you are configuring your operating system, often it has an impact on your functional code. For example, one solution to manage the operating system constraints is to put some slots for your functions and then make sure that your function does not exceed your slots. Yesterday, we had a very interesting presentation about the worst case execution times, and we've seen that it's very hard to obtain these worst case execution times, and it's even harder with multi-core processes. So what we wanted to do is to provide a mean to express your timing constraints, your segregation constraints, your safety constraints, and your error management constraints, and generate automatically all the tables you need to execute your code according to these requirements. So I will only focus on this part because, like I said, you already have your certification processes in place for your functional code. You know how to do this. But for the other part, usually it's manual. And we'd like to think that we provide some help on that. One major thing that I will present today is that everything I say about our technology is valid with single-core and multi-core CPUs. Everything is ready for multi-core, and we don't make any difference at operating system level between the two. Another very important aspect is that in our kernel, we don't have any locks, any mutex, or any semaphores, so everything is ready for multi-core, and it simplifies the analysis. Again, I won't go into details about the kernel today. If you want, we could discuss that outside of this meeting. But the main aspect is that we have a really simple real-time kernel, and we will need to generate the configuration for this kernel. First, you will have to provide us with timing constraints. For example, on top here, you will say that I have 3 functions, F1, F2, F3. They have to be executed sequentially. So the first is F1, then F2, then F3. And provide some timing constraints around them. So for example, I want F1 to be executed between the tick 0 and 1 millisecond. It means that I can make sure that the jitter on my function is managed. Then I want to execute F2, for example, between 0 and 4, and then F3 between 4 and 5. This is the kind of thing you will be able to express in our language. So you are not constrained to, let's say, periodic functions or harmonic functions. You can express any type of timing constraints at high level. By the way, agent is a name in our technology for task. So in another task, I know that I have to execute a function which is called here F4, and its constraint is between 0 and 4. And I know that they have to communicate at one point. So in this case, I want them to communicate on the point 4. It's not shown on the schematic. Based on these constraints, and whatever the complexity of your application is, we will be able to generate a scheduling table that fits all your requirements. So we will generate, for example, if your target is single core, then you put the 2 tasks on the same core. We will generate a scheduling plan for all your tasks, all your functions in your task, and make sure that if you provide us with some budget, and this relates to the discussion yesterday, if you provide us with some budget for F1, F2, F3, and F4, we will find a scheduling plan that fits your requirements. Then, if you go to a multi-core CPU, we will generate another scheduling plan, and then you can use the margins in the system for maybe evolutions, or maybe you can change your CPU and use a slower CPU because now you have time. What's important is you won't have to change anything in your code to move from your single core to your multi-core target. Everything is managed by the operating system, and the communication between the tasks is performed by the operating system. And it's responsible for the communication between cores, if there is any, or it's responsible to communicate between the tasks on the single core, if you want it to. All these communications are made lock-free, wait-free. Means that we won't have to provide analysis on locks or deadlocks in the system. Everything is designed to work seamlessly. This approach, we think, is unique, and we think has a great potential for certification aspects. Another aspect is your memory allocation, meaning some tasks will go in maybe internal RAM, some tasks will go into external RAM, and maybe you will have some design constraints. Maybe you will have to put this task in internal RAM, these other tasks in external RAM, or maybe you want to try. Maybe you want to try here in this example, task 1 in internal RAM, and then I want to try it in external RAM. We know that this will have an impact on your execution time. But the idea is that if you change your budgets as an input, again, you will have to estimate that budget, and this problem remains, but you already have this problem today. All you have to do is then recompile, and we will find a new scheduling plan for you in single core or multi-core. And also, we'll be able to provide when you will have interferences between your tasks, because we know which task is executed where. Most of these you can perform manually, and usually they are performed manually, meaning that usually what you do is write a static scheduling table, but each time you want to change something in your functions, or somebody comes with a new function, you have to redesign something. Usually you have to split your function, you have to put some additional code in your function, but it was not related. So what we want here is to have an automatic way to provide these scheduling tables and the memory protection of the computer, depending on your requirements and on the characteristics on the target. So we have a code generation tool. This takes as an input your spatial and temporal behavior. So like I said, your synchronization points between your functions. These will call external code. So you can write this code. Today, you can write it in C, but you could write it in Ada if you want, or in C++ or whatever. It depends on what you want. All we have to do is be able to link to your functions in some way. In this description, you will provide us with all the timing aspects, the synchronization points between the tasks. And they are independent from the target. You will express that you want to synchronize every 2 milliseconds, or if you receive some frame on the network, you will synchronize later on or earlier on. This can be simulated on a host PC, and you can validate this architecture very early on. It doesn't depend on the performance of your targets. Then you will provide us with some budgets for your target. You will say that this function takes this time and this other function takes this long. And we will provide you with some feedback on the margins you have on your system, and we will provide a scheduling table that fits all your requirements. The target configuration here is just some aspects like which task goes to which core, so it's a static allocation. In the end, we aim to provide some help allocating your agents to your core. Maybe you want to have some additional margins and so on, but for the moment, it's your job to provide this. And also the stack size, because this is a characteristic of your application. In this target configuration, you can also share data between agents if you want, or access other data. This is very specific, depends on what you want. For example, if you want a task to access some peripheral or something like that. Then we have our compiler, which we call Psycho for PsyCompiler, which takes some templates as inputs. These templates enables us to generate one given type of files. For example, today we generate C because we rely on a C cross-compiler as an output. So if we wanted to, we could change these templates to generate Ada, for example, and generate and compile your application with a cross-compiler with Ada or another language. So the first step of this compiler is to produce the configuration tables for the operating system that we provide. So mainly the scheduling tables, the protection memory tables, and the communication between the tasks. So today we have 3 categories. We have mainly data, which are the configuration tables, static configuration tables. We have the system calls for the task to go into the kernel. And we have the memory mapping, the linker script that will answer your needs in terms of function segregation that we have expressed at high level. Then you will provide us with your functional code, so your function that you have generated any way you want, manually or with code generators, qualified, not qualified, that's your problem. You can provide us with object files that you have previously certified, that's again your problem. And we will compile them using a cross-compiler on the market. Any cross-compiler that is compliant with your requirements and ours. In the end, you will have an executable object code. Today, it's a single ELF file, but in the future, we could generate any numbers of files if you wanted one per application or anything. Our strategy for qualification is a bit different from what has been presented before. We wanted to tackle this as checker tools. So we are using TQL5 tools, or we are creating TQL5 tools to check the output of what we produce. So we have made 3 types of checkers. It's just an internal code for us to simplify the categories of checkers. We have checkers that check the intermediate files in C. We have checkers that check the output, the ELF file, and we have a specific category for coding rules and, let's say, consistency of input. That's checker type 3. Checker type 1 will be responsible for mainly the scheduling part and all communication between tasks, buffers, size of buffers, and so on. Checker type 2 is mainly responsible for memory protection tables. So we check that the binary is correctly protected with the right access rights and so on. And also for everything that's related to health monitoring. So in case of error, I want to go into this state or in this state. This is checked on the final binary. The checker type 3 is just for checking the coding rules. So it's just to tick the box in the compliance to the DO, but it doesn't bring anything to the table on the functional side. Here is a more detailed view of what I've just said. SCI and key files are the files you've written to provide us with requirements. So SCI files are the one in which you express your spatial and timing constraints. Key files is the same, but for drivers. It's because the constraints are a bit different. Sometimes you want atomic accesses, so we have created a specific language for that. It's just a variant. We will check your user configuration, so your core allocation that you have asked that this task is on this core and the other task on the other core. So we have allocated your application correctly, that we have provided you with the right memory allocation, and also that it is consistent with your target, because we need to provide some kind of model of your target, which memory are available, which are the access rights that are available, and so on. The main point here is the scheduling is compliant with timing specification. This relies on formal mathematics models. We can prove that if your function respects its budget, then you will respect your real-time constraints, whatever happens in the system. So that's the key point. We check that the communication buffers that we have created for your tasks are rightly sized, meaning that we have created all the synchronization points correctly and that we have enough size in the buffer to store your data. And in the end, we have some configuration tables to synchronize everything, so we need to check that too. On the final binary, what we check is that the memory protection scheme is correct, meaning that we have the right sections on the right place and they are protected correctly. That we have not inserted any object code that you didn't want, and that we have provided the right object at the right place. And in the end, like I said, everything that's related to health monitoring, because we capture every single exception on the CPU to manage all the errors on the computer. So we need to make sure that it's covered. Like I said, the last point is the coding room checker, so it's just for the DO. In conclusion, we think that's an innovation because usually you don't have a formal way to express your timing and spatial requirements. Everyone has its way to do it, and usually you have a generator that provides you with an operating system configuration that fits your requirements. So this, on the functional side, this has been done for many years. People are doing them now. This is for functional, but you don't have anything for timing and spatial. What's important is that you will express your needs in terms of cadence, meaning what you expect from your system in terms of real-time behavior, not how you will do it on your target. And this is important when you are going to a multi-core CPU, because the interferences between the core will make it very, very difficult for you to find an operating system configuration that fits your requirement manually. And of course, another point is that we will provide you with some evidence for your certification, like offline sizing, that you have the right configuration for the target, that it's correctly protected, and then you don't have to check that again. So we are a small company, we are young, we have only 5 years, but we rely on experts from the domain to make sure that this strategy is sound. So we work with SCG Solutions, with Frédéric Poton, to build this strategy. And today we work hand in hand with Safran to make sure that, one, it answers the needs of the industry, in particular in your domain, And two, that they think that they could go into certification with our solution on single core and in the end in multi-core.